Hello guys, in the last video I told you about standing waves and the basic equation behind it. So y is equals to 2a sine omega t cos kx is the equation of standing wave. Of course it is different from the normal wave equation which was y is equals to a sine omega t minus kx. Standing waves are formed when two waves of similar amplitude move toward each other and they meet on a string. In general, standing waves can be formed on a tight string. If you have heard of the sonometer wire experiment, then I think you can understand this one. Otherwise also, if you have seen just a guitar string is a straight string bounded on two ends, correct? And we can set up standing waves in this string very easily. Let's say its length is L and its mass per unit length is mu. Okay, or simply let's talk about its length L only right now. So if we know its length, then the simplest standing wave would be if I hit it right here on the midpoint. Okay, if I hit it here with a tuning fork or with just a string, a basic wave will be created in this, which will look like this. The midsection will move downwards like this, and then it will come back and go above looking like this. The string will move from this position, a lower concave position, to a upper convex position, and it will go through various forms here and here also, and this will be the motion of the string. I can again remind you that these points, the point that do not move, are the nodes, and this point, the point which moves to a maximum extent, is an antinode. So a standing wave has nodes and antinodes, and it vibrates on its own position, correct? There is no transfer of energy from any point to other point. Say the starting point is A and B, so there is no transfer of energy from A to B. A standing wave just moves on its own position, and potential energy of particle converts to kinetic energy in this process. So basically, let's look at it mathematically. In this standing wave, you can figure out that this part of wave is like half of wavelength. This, correct? So only this much part is the part between A to B. We cannot see the rest of the part because when the fundamental wave, standing wave, is created in a string, the length of the string L is only equals to half of the wavelength lambda by 2. In this case, the length of the string is equal to lambda by 2. This is the basic mode of vibration for the string. I can name it as simply fundamental mode. Fundamental mode. In fundamental mode, only the length of the string is between point A and B, and we can clearly see that it is equals to lambda by 2. Now if we know the length of the string and we also know velocity, which is equals to under root T by mu, then I can calculate the fundamental frequency f naught is equals to v by lambda, and it will be equal to 1 by 2L, that is my lambda. From here lambda equals to 2L, and under root T by mu, that is my velocity. So f naught equals to 1 by 2L into root T by mu. You can simply remember it by v by 2L. So this is the fundamental mode of vibration for the string. And the fundamental frequency comes out to be v by 2L. So what if we want to create more loops here? Instead of just one loop vibrating, if we want to create more loops, then we will have to go to the next mode, which is called first overtone. First overtone is the mode in which we will create more loops between point A and B. This is point A, that is point B. Now I can see that I have made two loops between point A and B. In this situation, it is very clear to us that the length of the string is actually equal to the wavelength lambda, and the velocity remains unchanged because I am not changing the tension of the string right now. So velocity, if the velocity remains unchanged, then the new frequency f1 will be equal to v by lambda, that is nothing but v by L. This frequency, the frequency of first overtone, is twice the fundamental frequency. You can look here, f naught is v by 2L, while f1 is v by L, which is nothing but 2f naught. So the first overtone is twice of fundamental frequency. If a frequency is n types of fundamental frequency, it is called nth harmonics, which means the first overtone is also equal to the second harmonic. So this frequency can be called first overtone, or it can be called second harmonic. Whatever integer is in front of fundamental frequency is multiplied by fundamental frequency, that harmonic will be, that is the number of harmonic this frequency is called. So now you know the fundamental frequency and first overtone. The first overtone is also the second harmonic. We can do this again, and we can keep increasing the number of loops between A and B. And as we increase the number of loops, we will see that frequency will keep increasing, because V is always equals to f lambda for a wave. As long as we are not changing the tension in the string, we are not changing the velocity. And if we increase the number of loops, which means we are decreasing the wavelength, and if we decreasing the wavelength, we will increase the frequency. So that is the fundamental of sonometer wire experiment. Let me explain it to you in the next video.